Thanks for your introduction, Professor ICWE16, dear Professor Bori and Professor Bortolini. I'm very appreciative for your very much, for your kind invitation. Good afternoon, ladies and gentlemen. It's my great pleasure to have this chance to report to you the works on wind effects on large roof structures from Chongqing University Group. The presentation will including 5 parts. Now let's begin from the background. Large roof structures such as sport venue, transportation harbors, and exhibition centers are widely built around the world. Well, wind-induced damage to this kind of large roof structures occurred often around the world, such as in America, Japan, China, South Korea, and so on. Large roof structures are usually grouped to the cable membrane structure, which is a flexible, soft structure, and steel structures. The steel structure usually including 2 parts. One is the cladding and the components, and the main frame structures. Different kind of structure are with different dynamic properties, and the wind-induced effect and damages are different also. I will show you all of them. The cable membrane structure is prone to be damaged by strong wind, and the progressive damage usually occurred. It's believed that wind-structure interaction is a significant factor for the damage of the membrane structures, as it is low stiffness. For the roof cladding and components, wind-induced damage is very common, actually also very heavy. It's the main concern of the engineers. Wind-induced dynamic effect of the claddings can be ignored due to the high stiffness of the small-sized force-bearing unit. So, the accurately estimating the extreme wind pressure and the load-bearing capacity are the key issues to keep the structure safety. For the main frames, the damage feature of this kind of a roof is the over-limit vibration and sometimes even collapse. Wind-induced vibration effect needs to be considered in the design, and the design wind load is usually expressed as equivalent static wind load. From the background, we think there are some key issues should be solved. As elastic tests showed that the wind structure interaction may lead the response of a sudden dramatic increase and the model jump. Well, the underlying mechanism of the wind structure interaction effects hasn't been cleared yet, and the analysis methods haven't been found to be reported also. For the claddings and the components, to keep them safety, we should let the resisted capacity smaller than the wind load. For the wind load, we should examine or estimate the point pressure and the area pressures. For the resistance capacity of the cladding and the components, the main concern is the joints and the purlins. For the point wind pressure, the extreme value of the point wind pressure, the layout of the pressure taps in wind tunnel tests needs to nicely capture the characteristic of the flow. Pressure taps are often arranged subjectively by experience in our wind tunnel tests, while quantitative criteria are needed for checking the rationality of the pressure taps arrangement and to reduce the pressure gradient of the adjacent taps. The damage of the cladding and components usually induced by the large extreme value of the wind pressure of the non-Gaussian process occurring at the leading edge, and the key concern is to calculate the peak factor. Accurate and efficient method for calculating the peak factor is needed in engineering and is a challenge to be satisfied for different kinds of non-Gaussian distributions. For the area wind load of the cladding and components, the extreme wind pressure over all directions should be considered for the wind load on the claddings, which usually is especially uneven distributed. Objective zoning method is desired to balance the safety and the cost. Extreme wind pressure of the adjacent taps vary greatly with a big gradient will occur at a different time. Both the correlation and the gradient should be considered for the area reducing effects, while the influence of the gradient haven't been studied enough so far, I think. For the wind resistance capacity as the metal envelope system or extensively utilized in the large roof structures for the excellent waterproofing and the convenient construction, etc. The claddings usually are composed by multiple layers of components and C or Z sectional purlin with complicated connections. So the local failure mechanism of the seam and clip connections is complex and not clear yet, and the purlin buckling, considering the diaphragm effects, is also difficult for the engineering design. For the main frame structures, there are many kinds of structures. Their characteristic of the wind-induced response are much different, as their dynamic properties have a big difference, such as for the flat roof. For the flat roof, usually they have one dominant mode. For the cylindrical roofs, usually have two dominant roofs. But for the dome roofs, we call it three-dimensional space structures. Each mode gave only a small contribution to the response. There are many models give the contribution. So it's difficult to find the dominant modes. So method analyzing wind-induced response of this kind of space structure is desired. For this kind of space structures, this with low stiffness, low damping, and vibration with multiple modes. The dominant mode may appear in the higher order. Even the dominant mode gave a very small contribution. For this case, it is only 5%. So traditionally, the higher order modes are easily overlooked. So it's necessary to select the dominant vibration mode to calculate a wind-induced response with high efficiency. This depends on the correlation of the vibration modes and the wind load distribution. Well, for the wind load distribution as a very special and temporal distribution of the fluctuating wind load results in no specific distribution form. There was no method for selecting the dominant vibration mode. Yeah. Next is for the equivalent static wind load. Sorry. Yeah. This is for the equivalent static wind load. The number of the equivalent targets of the space structures is usually big, and the number of the equivalent static wind load are also big, which makes the engineering design very inconvenient if single target equivalent static wind load method is adapted. So the universal equivalent static wind load is needed very much for large space structures. So I will, in the following three sections, will focus on these issues one by one. First, I will introduce wind structure interaction of membrane structures. To reveal the interaction mechanism of the wind and the membrane structures, the aeroelastic appearance are accurately reproduced by the fully coupled numerical simulation. The wind-induced response of the tension membrane are accurately simulated. The mode jump of the membrane structure, this kind of phenomena, is also reproduced in the CFD analysis. From the CFD analysis, it is found when the wind load or the wind velocity is low, the shading and the convection of the vortex above the membrane surface are stochastic and irrelevant with the vibration itself. But when the speed increases, after the mode jump occurs, the vortex shading are resonant with the vibration, and the vortex convection are synchronized with the uplift motion. Yeah, maybe you can see that. Huh? This point always, the vortex is coincide with the uplift of the membrane motion. That indicates that the wind-induced vibration of the membrane structure is a kind of vortex-induced vibration. Furthermore, the wind structure interaction effect of three-dimensional membrane structure are also analyzed. From the result, it is shown that the wind pressure on the middle area are significantly increased due to exist here is much bigger than this area and the existence of the wind structure interaction effect. The separated vortex, which formed at the leading edge above the rigid structure, may shift toward to the middle or the trailing zone for the vibrating structure. This is the reason that caused a notable increase in the wind pressure. To establish the wind-induced response analysis method, considering this kind of wind structure interaction effects, the motion-induced aerodynamic forces should be identified. This kind of motion-induced aerodynamic force, as all of you know, usually expressed by the aerodynamic force, damping, and the stiffness. The aerodynamic damping and the aerodynamic stiffness may be identified based on the forced vibration method. This is the result for the identification. We can see that the aerodynamic stiffness is a constant at a given reduced wind velocity, no relation to the response. Correspondingly, we call this a linear aerodynamic stiffness force, which can be directly substituted into the analysis equation, the motion equation. Well, the aerodynamic damping is positive in the lower reduced wind velocity, which will decrease to negative in a higher reduced wind velocity. So the aerodynamic damping is a nonlinear function of the amplitude. To analyze the structural response, an appropriate model describing the nonlinear relationship between the aerodynamic damping and the structural response is needed. It is found that this kind of nonlinear aerodynamic damping may be actually modeled by the generalized, we call the generalized van der Pol model, is proposed by our group. The response of the membrane structure with nonlinear aerodynamic damping usually is unsolvable. But we can transfer it to a solvable nonlinear system, such as the FPK function. If we do so, we can obtain the probability density function of the structural response. If we get the PDF, then the standardization hypothesis, peak response, and peak factor can be calculated. This gives an example result, what we obtained for membrane structure. The structural response gradually transists from the Gaussian distribution to a non-Gaussian distribution with the increasing of the wind velocity, along with a rapid increase of the structural vibration response. Well, the cortices and the peak factor are decreased. This is what we have done on the membrane structures. I want to give a short summary. The wind-induced vibration and the modal drop phenomena of the membrane structure are reproduced based on the fully coupled simulation. And the wind structure interaction of the membrane structure is found to be a kind of vortex-induced vibration. A nonlinear motion-induced aerodynamic force model of the membrane structure is proposed based on the generalized van der Pol model. An equivalent nonlinear method for estimating the wind-induced response of the membrane structure considering wind structure interaction is established. This kind of research, the result we applied to some engineering projects. Actually, we directly do the consulting work for more than 30 membrane structures, also the important and big project. Next, we go to the cladding and the components. Pressure tests are often arranged by subjective experience, as just mentioned, which is correct qualitatively. Well, a objective and quantity evaluation criteria for the sufficiency of the taps is proposed by the wind pressure coefficient between the jacked taps. Usually they have this two kind of result. Sorry, there's some mistake. Some area satisfies this kind of sufficiency requirement. There's no treatment is needed. If some not satisfy the criteria, also have two cases. One is this even not satisfy the criteria, but close to that criteria, we can use the interpolation method to give intense type point. If not close to the criteria, maybe you should add the more taps and reconduct your wind tunnel test. For the port that can be interpolated, the Qingshan method and the POD method, for example, can be applied respectively to interpret the mean wind pressure coefficient and the fluctuating wind pressure coefficients. For the interpolation, adaptive interpolation method is developed to arrange interpolation point according to the wind pressure difference between the Jackson taps to meet the sufficiency requirement of the pressure points. Here we show some of the result. After we get the time history of the wind pressures, the extreme value of non-Gaussian wind pressure coefficient can be estimated by type 1 or type 3 distribution. If the time history is long enough, more efficient ways with a short time history are also proposed by the pioneer researchers. The translation process method based on the peak factor of Gaussian process is widely applied. The moment-based Hermite model of the translation process method based on the first 4 moments has been widely studied. Its accuracy sometimes, and some cases, not satisfied, and the sampling error exists, not known yet. So we do some further analysis on the PDF of the pressure process. We find the tail, because we concern the extreme value, so the tail of the probability density is very important to us, is sensitive to the skewness. In different way for left and right side tails. When the skewness less than 0, the skewness will control the right tail, and the left tail is not sensitive to it. When the skewness bigger than 0, the skewness controls the left tail, the right tail is not sensitive to it. So after this kind of consideration, the idea is to abandon the parameter skewness by reconstructing a process by using the measuring to divide the PDF. Thus, the skewness of a new process is always 0. The reconstructed zero-skewed process doesn't change the original tail property. If we use a new construct process, we can get a much better result compared to the original process. This is the arrow by the original process. They have the arrow was big in this area. This is for the reconstructed process. The higher arrows missed. all of them have a great improvement. For the sample error of the estimated peak factor may be represented by the coefficient of the variance of the peak factor. Actually, traditionally, the controlling parameters was given only for white noise process. But when the pressure process, which is not white noise, but correlated, so we propose the method for the determine the control parameters for this kind of wind pressure process, considering the autocorrelation. The sample error has been estimated by the proposed method and is compared with that calculated by the long observed data. The observed data is 270 sets of 10 minutes length wind pressure. And the economical sample length of the wind pressure can be determined by the proposed method. The sample error in terms of COV of the peak factor decreased 40% when the sample duration increased from 10 minutes to 30 minutes. This is important for us to get the sampling in the wind tunnel test. For the area wind pressure, traditionally was zoned based on the subjective experience, which is correct and qualitatively. A more objective and accurate method is proposed by the weight clustering method, which is a data-driven method. They have some advantages, we think, that the spatial location and the pressure value of each type is considered at the same time. And the importance of each variable is balanced in the analysis by assigning a weight factor. Compared to the empirical zoning method, the proposed method may give objective results quantitatively for both the simple and complicated pressure distribution. The influence of both the gradient and the correlation of the pressure on the area reduction effect can be effectively taken into consider by interpolation. The procedure is the same, but we use the more dense pressure value, we can get a more accurate result. This side is an area reduction curve. Are different for with and without this kind of interpolation. It is found that the traditional method underestimates high pressure in some small areas, overestimate low pressure for the big areas. We make a very bad design. Is expensive, will sometimes also dangerous. So use interpolated data is very important, we think. For when the resistance capacity was joint of the roof of claddings, the wind-induced pull-out failure standing seam metal cladding system is sketched in this figure. It is shown the seam clip connection is the port susceptible to the wind uplift effect. And there are two failure models. One is the seam clip failure and the seam to seam failure. Actually, there are many researchers and investigations on this kind of wind-induced response of cladding and components by the pressure temperature test, by wind tunnel test, and some joint test. Well, also by the refined finite element analysis. But we think there's still some work need to be done. An equivalent spring model was developed for this kind of claddings to simplify the highly nonlinear contact boundary condition based on the pull-out failure mechanism. The developed model comprising continuous rotational and horizontal springs was employed to simulate the mechanical performance of seam and clip connections. Here we get the horizontal mechanical behavior by the tensile tests. By this kind of test, we can determine the horizontal stiffness, which can be calibrated the relationship between the rotation angle and the moment. By the same way, we can also get the rotation stiffness. The equivalent spring mode of the seam clip connection was validated by the substructure test. From the test, it defined the developed model for evaluating the structural response of the system is feasible and accurate. The next, we want to determine the controlling parameter of the pull-out failure of this kind of structure. The failure model, the seam clip failure model, is caused by the high reaction force of the clip, which can be identified as a controlling parameter of the seam clip failure. For the seam failure model, is caused by the large rotation deformation of the web, which is controlling parameters. After we get the metal sheet, the wind pressure will, through the metal sheet, transfer to the purlins as the components of the roof. This kind of purlins usually use C or Z sectional components. The buckling model of this kind of purlin should considering the diagram effect under eccentric wind uplift. Well, in the previous study, this concept not accepted because the rappelling torsion effect was not considered. So we derived a new equation about this kind of structure and this kind of wind load. The new differential equation considers the coupling of the load eccentricity and the diaphragm effect. The stress of the bending plus rappelling torsion and the local buckling model are obtained. After you get this kind of research result, we transfer that to the design method. So the modified direct strength method for the purlin sheeting system design is proposed. Here we give some formulas. I will not give the further explanation. Well, this formula was validated by the global available test data obtained in the past 3 decades. To make sure the design method is accurate and be safety. Then we go to give a summary about the cladding and components. Extreme wind pressure coefficient estimation. In this part, an objective quantity criteria on gauging the sufficiency of the wind pressure taps was established, and an adaptive pressure interpolation method was proposed, and the piecewise moment-based hermetism was proposed, and sampling error estimating method and the advice when the internal test period was provided. For the area loading, an objective load zoning method was proposed. an area reduction method, and considering both gradient and correlation has been proposed. And we also studied the resistant capacity of the roof and the components, established the equivalent supreme mode. Now we go to the main frames of the roof structure. As also we mentioned, it is necessary to take into account many vibration modes to calculate the response. The mode of contribution depends on the correlation between the loading and the vibration mode. So we use the POD method to decomposite the fluctuating wind pressure to the load engine modes and check the correlation between the load engine mode and the vibration modes. If their correlation is strong, that will be the dominant vibration mode. So the proposal selecting the dominant mode and analyzing wind-induced response of this kind of space structures is called RIS POD method. And we applied this method to this kind of dome structures. The results show that using the first 10 dominant modes reach the same accuracy with 60 natural vibration mode. The computational efficiency may improve by over 60%, and the improving may increase with the increase of the structure scale. Next, for the space structure, we consider the universal equivalent static wind load. And many modes contribute to the response, and the dynamic response at each point usually do not reach the extreme value synchronously. Universal equivalent static wind load is needed for improving the design efficiency, as mentioned before. The method of calculating universal equivalent static wind load for space structure is proposed based on the dominant load engine mode and the structural mode following the work of Professor Tamla. Here, the fundamental distribution composed by the engine mode and the model inertial force. For this case, the universal equivalent static wind load for multi-target load effects can be expressed by this, the first equation, and the response of the universal equivalent static wind load should meet these equations. The response of the universal equivalent static wind load should be the multiple dynamic peak response. What we want is to get the combination factor, which can be obtained by this equation. But usually, the combination factor has only a least square solution. Anyway, we can get the combination factor. After that, the universal equivalent static wind load is obtained. When we calculate the response, we should also add the mean wind load. Here we use this method to many different kind of real structures. This Olympic Sports Center, the members totally 16,000. We use one universal equivalent static wind load can reach the peak response of these 16,000 members. For the second one is another structure. We give the effect of the displacement. It shows that the accuracy for displacement is better than the membrane for member structures, member stress. From these two practical building, response and equivalent static wind load agree well with the actual dynamic peak response. as we mentioned before, that for the large roofs, we can use many different kind of structures. Even for the same shape, like a flat roof, we can use a beam and a truss and a spatial truss, different kind of structures. And for the cylindrical roofs, you can use arch or shells. Both can reach you can design different kind of structures. So we do some parameter analysis for these kind of structures, especially for the mean velocity, for example, mean velocity, wind direction, spans, rise span ratio, roof mass. We over 2,000 cases study. We get some empirical results. Here show some pictures for the wind tunnel test for the cylindrical roofs. Here, L is the span, B is the length, aspect ratio, and F is the rise span, the height of the rise, and L is the span. This is also for the dome structures. After the numerical analysis, we can get the wind load for different kind of structures. For this kind of plain truss or beams, here we give the first part is the mean wind load. The second is the equivalent static wind load. The equivalent static wind load can be use this formula. Here is the amplitude, which is a function of the reduced frequency, defined by the first mode frequency and the roof span and the incoming mean wind speed. Here we analyze the different kind of wind direction, and for the structure, if in the different part, maybe they have the different parameters. This is the result for the plain truss and beams. In the same way, you can obtain the flat spatial trusses. And plain arch truss can be used arch roofs. And this kind of cylindrical shells. And also for the dome shells, lattice shells. Yeah. The above results become the main constraints of the standard for wind load and roof structures of China, which issued in 2019. In this standard, we give the extreme area wind pressure and cladding and components in this different kind of shape of the roofs. Also give the universal equivalent static wind load for the roof structures or the frame structures for different kind of shape and different kind of structures. During the years, we also involved many engineering projects about the transportation harbors and stadiums. Maybe if you join the ICWE16, you maybe visit this structure is the China National Stadium and some other. All this in the Olympic Park. This structure all in the Olympic Park. And also many exhibition centers. Also we will do some international projects out of China overseas. Yeah. I want to go to the brief summary. The wind structure interaction of the membrane structure analysis. A non-Gaussian stream wind pressure evaluation method and a zoning method based on clustering are proposed. A simplified calculation model of the metro enclosure system are proposed. An efficiency analysis method for multi-mode when the induced vibration response and the universal equivalent static wind load analysis method are proposed. For typical roof structures, the calculation charts of the extreme wind pressure of cladding and components and the universal equivalent static wind loads of the main frames are given for design. These are included in the China standard for roof. That's all for my presentation. Thank you very much. Thanks for your attention.
Thank you.